People, hope we're doing well today. In these videos, we're going to be exploring vector value functions and the application of integral calculus to those. And first, on these first couple of problems, what we're going to do is we're just going to kind of deal with the mechanics of it and show that just like differentiation as it's applied to vector value functions, we're just going to do it component by component, okay? Now, when we when we integrate cosine of pi t and sine of pi t, remember that that's pretty much going to be just like cosine of 2t, or if we were dealing with it in terms of x. The way that you would integrate cosine of 2x would be 1/2 and then a negative sine of 2x, okay? Or actually positive sign, because cosine would be the derivative of, right? So we're going to do it the same way, and the pi shouldn't distract us, but because it's pi, it's likely to. And so if we're doing this first one, basically we have sine of pi t divided by pi I, and it's the I component, that's the horizontal component. And then this next one is sine is the derivative of negative cosine. So this next one is negative cosine pi t also over pi j plus c, right? It is an indefinite integral. Now, I like to do things in I don't like unit vector form, I like component form. So the way that this could be written in component form is the integral of cosine pi t dt and the integral of sine pi t dt. And I like this better because it just makes a little more sense. You don't have this c dangling out there, unsure, what portion of it goes towards the I and what portion of it goes towards the t. This one gives you sine of pi t over pi plus c1 and negative cosine pi t over pi plus c2, okay? And basically, I always work in component form. If it's given to me in unit vector form, I always convert it over to component form and then go back. There's a risk there. You could forget to go back because, of course, the answer that you're supposed to give should be in the form that it's given. But you're going to have to make the evaluation as to whether that's appropriate or not. Let's go ahead and, again, put this one into component form. This would be the same thing as breaking it up into the two integrals, one for the horizontal component, which is the integral of 0 to 1 of 4 over 1 plus t squared dt. And if you're saying, hey, this looks familiar, yeah, we did the majority of this one in class, but I thought I would just sort of memorialize it here on the videos as well. Now, this one right here, we're going to deal with, go ahead and deal with both of these like this. So it becomes arctan of t, but of course 4 arctan of t, evaluated from 0 to 1. That becomes 4 arctan of 1 minus 4 arctan of 0. That, of course, is 0. And you get 4, and arctan of 1 is pi over 4, so this just becomes pi. This, of course, is the natural log of 1 plus t squared. We're going to be doing it from 0 to 1. And that's going to be the natural log of 2 minus the natural log of 1. And thankfully, just like the last one of those terms is 0. And so I just get the natural log of 2. Now what that means is I get pi natural log of 2, or in unit vector form, I'm going to get pi I plus natural log 2 j. And there is my answer. Okay. Well, that's all well and good, but let's actually get to, more than just the mechanics. Now, remember way back in the day when you were first being introduced to antiderivatives, you were given problems like this, where you were given f double prime, and you were given a condition on f and f prime, and asked sort of to work backwards, right? And so if you have f double prime is equal to 8x cubed plus 5, then we know that f prime is going to be 8/4, right? Because this is going to go to x to the 4th over 4, so it becomes 2x to the 4th plus 5x plus, and we'll call this C1 since we know we're going to do it twice. Now, what happens here is I need to take this condition and plug it in. So if I plug in 1, I'm going to get 2 plus 5 plus C1, and that should be equal to 8, which means C1 is equal to 1. Okay, well that allows me to get to f prime of x is equal to 2x to the 4th plus 5x plus 1, and we go ahead and anti-differentiate, and we're going to get 2/5 x to the 5th plus 5/2 x squared plus x plus C2. Now we're going to use this condition in order, basically that ordered pair, in order to solve for our C2. The output is 0 when I plug in 1, which makes the arithmetic actually really easy. When I get a common denominator of 10, this is going to be 4/10, this is going to be 25/10, this is going to be 10/10. Together that's 39/10, and therefore C2 is equal to negative 39/10, right? Because you have to sort of, push it off to the other side. And therefore, using that f double prime and the two conditions that I was given, I can surmise that f of x is 2/5 x to the 5th plus 5/2 x squared plus x minus 39/10. Now, you're sort of wondering, why in the world are we reviewing that? Well, what we're going to be doing in the next couple of problems is actually rather similar. It's basically the same logic, just applied for vector value functions. So let's go ahead and do that. Now, if I'm given r, if I need to find r, but I'm given r prime, and of course r prime in component form is going to be sine t negative cosine t. Well, if that's the case, and I can integrate or anti-differentiate term by term, I know that r of t is going to be basically the integral of, or the antiderivative, right, of sine t and the integral of negative cosine t dt. Well, that's easy enough. Sine, of course, is the derivative of negative cosine t, and we'll go ahead and put the plus C1 right there. And then, of course, we have cosine is the derivative of sine, but we have this negative that comes along for the ride, and we have sine t plus C2. Now, remember that this right here in component form is 1, 1. So basically, if I were to plug in 0 for both of these t's, I should get 1 and 1, and that is going to help me solve for C1 and C2. So basically, I need r of 0 is going to be negative cosine of 0 plus C1, negative sine of 0 plus C2, and that needs to be equal to 1, 1. Well, obviously, cosine of 0 is negative 1. So negative 1 plus C1 is equal to 1. So C1 is equal to 2. Negative sine, well, this winds up being 0. So C2 is just equal to 1. And therefore, what we have here is we have r of t in component form is negative cosine t plus 2, negative sine t plus 1. But in unit vector form, 2 minus cosine t I plus 1 minus sine t j. Wow, almost ran out of room. And there you go. Now, this next one is similar. It says a particle moves in the xy plane in such a way that its velocity vector is 1 plus t and t cubed. Now, if the position vector at t is equal to 0, okay, well, that's another way. Basically, this right here is another way of saying, right, r of 0 is equal to 5, 0. Find the position of the particle at t is equal to 2. Well, in order to get to r of t, I'm going to need to integrate 1 plus t dt, and I'm going to need to integrate t cubed dt, and that's going to wind up being t plus 1/2 t squared plus c1, and 1/4 t to the 4th plus c2. Well, you don't have to do c1 and c2 if you don't like subscript. I guess you can do c and d or whatever. I mean, there's no magic to what you're calling them. But let's go ahead and take the initial condition and find our c1 and our c2 so that we can actually answer the question. So we have r of 0, and that becomes 0 plus 1/2 0 squared plus c1, and 1/4 0 to the 4th plus c2, and that should be equal to 5, 0. Well, that's 0, that's 0, that's 0. So basically c1, in this one, no arithmetic involved at all, and c2 is equal to 0. So once we've used our initial condition, we have a complete position vector function, and therefore we know that it is, and I'm going to go ahead and put this first one in descending order now that I have my c1, and this one winds up being 1/4 t to the 4th, and now all I have to do to find the position of the particle at t is equal to 2 is just evaluate this at 2, and that winds up being 1/2 1/2 t squared, okay, at which point you're going to plug into 2 squared times 1/2 is 2 plus 5, and this is going to be 1/4 times 16, and the answer, of course, is 9, 4. Now, of course, it was given to me in component form, so I felt comfortable actually answering it in component form. But let's go ahead and move on to another one. Okay. Find the velocity and the position of a particle that has the given acceleration and the specified initial velocity and position. So basically, this is kind of like being given f double prime and doing those 2 iterations back to f. In this case, I'm being given the acceleration vector, and I'm going to have to first get back to the velocity vector and then solve for c1 and c2. And then I'm going to have to use that velocity vector to get back to the position vector and solve again, okay? So I'm going to go ahead like I am wont to do, and I'm going to turn this into component form. Now, that means, sorry, I should have put a t right here, but you get it. V of t is equal to the integral of 0 dt and the integral of -10 dt. Well, what is 0 the derivative of? Well, just the constant, okay? And this next one becomes -10t plus c2. Now, velocity vector right here is basically, this right here means that v naught is in component form 1, 1. So if I go ahead and plug in 0, I'm going to get c1, c2 is equal to 1, 1. And again, it's one of those nice ones where there really is no arithmetic to do because everything else kind of disappeared. And therefore, my velocity vector is going to be 1 and then -10t plus 1. Now, I have gotten to here, and now I need to get to the position vector. So I need to anti-differentiate again. And so what we have here is my r, and I know my r's look like my v's. I should really do something about that. Maybe I should use capital R's or something, but this is r, and that's a v. What happens here is I need, the antiderivative of 1 dt, and I need the antiderivative of -10t plus 1 dt, which, shouldn't be too tough. The antiderivative of 1 is t, and on this one I'm going to use d for it, so d sub 1 and d sub 2. Now, of course, the antiderivative of -10t is -5t squared. Antiderivative of 1 is t, and then, of course, I have to tack on a d2 for the constant, the constant that's possibly there for this component as well. Now, up here, this r of 0, if it's the 0 vector, then it's 0, 0. And therefore, if I'm going to plug in 0, I'm going to get 0 plus d1, and negative 5, 0 squared plus 0 plus d2, and that's going to be equal to 0 and 0. Well, that's 0, that's 0, that's 0. Again, I have ones that don't actually require any arithmetic, and that's kind of nice, which means that my position vector is just this without the d's. So it's t and negative 5t squared plus t. Okay, and I have basically gotten what it asked me to. I found the velocity vector, and I found the position vector. And from there, of course, if it asked me anything else, it would be pretty easy to go ahead and find those. Like if it asked me for the velocity vector at t is equal to 3, I would just plug in, right? Okay. Now that's a lot of mechanics in terms of just doing it component by component, and of course using initial conditions in order to anti-differentiate and solve for the constants that are possibly there. Now, what does this mean for the application of vector function integration? Okay. And that question will be how we start off in video number 2.